Hello and welcome to this presentation on ArgoTweak, towards self-updating maps through structured priors. Let's begin with the core question. How can autonomous vehicles understand the road? We might start with a simple approach. Place sensors on the car and use their data to infer a local map. This method is attractive because it's relatively cheap and always up to date, but it has limitations. Sensors are noisy and occlusions inevitably degrade the quality of the map. An alternative is to rely on HD maps. Once localized within them, we gain access to rich pre-computed knowledge. However, HD maps come with their own problems. They can quickly become outdated in our ever-changing dynamic world, and they're expensive both to acquire and to maintain. So, what if we could combine the best of both worlds? Imagine fusing HD maps with sensor data, then using that combination to detect outdated map parts and update them. That way, the vehicle always drives with an accurate road representation. To train such a system, we need the right kind of data set. An HD map to start with. Then construction work occurs, making it outdated. We hence need up-to-date sensor data and a new ground truth map. Unfortunately, existing public datasets don't meet these requirements. As one can see in the table, none include the essential triplet. That's why our first major contribution is the ArgoTweak dataset. We built on top of Argoverse's Trust but Verify split. For testing, we use stale map features plus sensor input while re-annotating the missing ground truth maps. Since stale maps are rare and don't exist for training and validation, we create synthetic ones by hand with high realism. We do this by building a custom map editor, which lets us load lane segments, their attributes, aggregated LiDAR frames, and then tweak maps directly. This process produced nearly 1,000 highly realistic or real-world maps. With the dataset in place, what model do we need? We start from a standard online HD mapping paradigm, but instead of pure map perception, we focus on map updating. To do this, we use the stale HD map encoder and then add change detection heads. These heads allow us to not only update the map, but also explain the nature of changes, insertions, deletions, geometry changes, and more. This emphasis on explainability is crucial. Why? Because it changes how we evaluate performance. Traditional evaluation has a shortcoming. Consider the following example. We have sensor input and a stale map. In ground truth, the rightmost lane has been converted into a bike lane. Now imagine two networks. Network A barely updates the prior, while Network B responds well to the change, but slightly degrades the overall map. Traditional evaluation would simply compare elements one by one, averaging them into a single score. This approach masks important differences. Network A is stable on unchanged regions, while Network B shows responsiveness to changes. Both aspects matter, and that's why we argue that only explainable models trained on explainable datasets and evaluated with explainable metrics can disentangle these meaningful distinctions in behavior. To support this, we introduce a bijective mapping framework. The key idea is to take large-scale road changes and break them down into atomic element-wise modifications at the element level. However, annotation is not straightforward. We could choose to annotate it like this, or like that, or even like this. Hence, our bijective mapping framework is needed to ensure that every large-scale change can be meaningfully explained at the element level. The key components are surjectivity, which ensures all changes can be described in this atomic vocabulary, and injectivity, eliminating all but one annotation variant and hence removing ambiguity. This guarantees that every large-scale change has a single, precise explanation. When we put everything together, we see that only models trained on ArgoTweak update maps meaningfully. And our quantitative evaluation shows that we reduce the sim to real gap by a factor of 10 compared to training on simple rule-based priors. This highlights both the realism and the strength of our dataset, laying the foundations for explainable, lifelong HD map updating. For further details, please check out the paper and don't forget to visit our dataset page. Thank you.